Okay, so it's being recorded now.
Okay. So thank you very much for the introduction. It's very nice to be here today. I wanted to ask how do you hear me? Is my voice clear? Yeah, everything is fine?
Yes. I guess
you can see the slides.
with the listeners, mute the microphones.
Yes, this is always helpful. So thank you very much for inviting me here. I'm super excited and a little bit nervous, to do this presentation. And let me start. So I would like to start talking a little bit about myself so that you know who I am. So I was born in Tbilisi in 1981. And from 87 to 98, I studied at 76 Middle School of Tbilisi, which is in the airport region. Then in 98, I embarked on studies at the Faculty of Applied Mathematics and Informatics at Tbilisi State University. So I always call it Mchedlize because it was about visiting the Mchedlize building, which is so special. In 2000, because of my origin and my good grades at school, I managed to get a scholarship to study in Greece from Ministry of Foreign Affairs, and I moved to Greece, so a little bit to the south, west and south. And for 1 year, I had to learn Greek because I didn't know any Greek, and I was learning Greek. And then in 2001, I started studying at Applied Mathematics and Physics, Faculty of Applied Mathematics and Physics at National Technical University of Athens. So don't ask me why physics. It was the closest to the faculty in Georgia at that moment. So I wanted to study applied mathematics, and whether it was physics or computer science didn't matter for me at that point. Then I finished in 2006. The study lasted for 5 years, and I managed to finish in 5 years, which was very, very hard. But I managed. And then for 3 years, I did my master's at the same faculty. And at the same time, I was working as a software engineer in a company, which actually gave me a very good idea that I actually want to do research. I didn't want to work in academia. And in parallel to my master's, I started a PhD. And I finished my PhD in 2011, and the topic of it was graph theory problems with emphasis on graph drawing. So I worked both on graph theory and on graph drawing, looking at the algorithmic aspect. In 2012, I moved to Germany, to Karlsruhe, and been there for 8 years in the group of Dorothea Wagner. And I expanded on graph drawing to multiple perspectives, not only algorithm, and I will talk about this a little bit more. And since 2020, I'm assistant professor at the Department of Information and Computing Science at the Utrecht University. And now I am actually not in theory group anymore, but I'm in the visualization group. So I'm considering even more applied aspects now of graph drawing. So now, a little bit about my talk today. I will start defining the field of graph drawing and network visualization so that you get a good impression of what the whole field is about, what does it study. Then I will talk a little bit about my research in the field. And then I will concentrate on a small part of my research and talk about some geometric problems, which are called point set embedding. And at the end, I will give you one proof. Yeah, so one problem and one proof, so that you get a good idea of what are the details of the field. So probably all of you know what is a graph. Yeah, so a graph is an abstract structure which consists of some set of elements. We call them vertices, and some pairs of those vertices, which we call edges. Yeah. By the way, when I mark my screen, do you see it? Do you see when I'm marking?
Yes. We do.
Okay, excellent. Yeah, so we have those vertices and those pairs of vertices, which we call edges. And this composes the structure of a graph. So here is an example. Yes, so we have a set of elements, and we have a set of pairs of those elements. And of course, if we just have this graph in this textual form, we cannot understand much about it. Yeah, it's very hard. But what we can do, we can actually draw it. we can just draw it on a paper, right, on the plane. We can depict our vertices as some small circles or points, and then we can depict the edges by curves, lines, polylines, or real curves connecting the edges, the vertices. So this is just a random position of nodes. We just put them on the plane as you know, as we wanted. But if we try a little bit more, so this is exactly the same graph. If we try a little bit more, then we can actually get a visualization, a drawing of a graph, which is much more readable. So we can start making sense of it. A little bit of history. So graph drawing is a very, very old field. This is a diagram from 1516. And what it depicts is a different state of soul and transition between those states. Apparently, people thought in these abstract terms already in 16th century. This is, again, from 16th century, these different geometric notions and how they interact. And this is much more modern to just show that graph drawing appears everywhere. This is UML diagram. Yeah, so we have our nodes actually classes. Yeah, and you know the boxes describing classes, and then we have the edges which depict the interactions, you know, the inheritance between the classes. Probably you cannot see this picture very well because this is a very, very large network, which is impossible to show on one slide, but I can zoom in a little bit. This is a very interesting network of different Faust editions. Yes, so different Faust have been written in multiple phases, and these are all different editions, and the edges are actually which edition precedes which. It's a huge network, very, very difficult to visualize. So in order to study graph drawing problem formally, yeah, so I'm a mathematician in my background, and of course I want to study graph drawing problem formally. Therefore, I have to look at the formal definition of the problem. So how do I formalize it? And let me start with something, you know, very, very high level. I'm given as an input a graph, yeah, and what I want to find, yeah, if I look at it algorithmically, I want to find a good drawing of the graph. So first of all, what is a drawing? Yeah, I can define it mathematically. The drawing of a graph is a mapping of vertices to points on the plane and of edges to curves. Yeah, and here is you know, the precise definition saying that the curve should to connect exactly those vertices which it's supposed to. This is a formal definition of a drawing. But what is a good? Yeah, so this is much more complicated to define. And over the development of the graph drawing field, researchers came up with 3 ways to formalize it. Yeah, so 3, let's say, aspects of this formalization. And let me start with the first. The first is so-called drawing conventions. Yeah, so these are the rules which actually stem from applications. For instance, all the edges have to be straight lines, yeah, or all the edges have to follow a grid. Yeah, this, for instance, for UML diagrams, yeah, they want to be drawn, you know, from application, it comes that they want to be drawn this way. Or for chip design, yeah, also the edges have to follow a grid. For instance, we want that the edges don't intersect, yeah, also comes from a chip design, yeah, so we may require that our edges don't intersect. So this is kind of very hard rules, absolutely hard rules that the output of the algorithm has to satisfy. Yeah, we call them drawing conventions. Then there is soft constraints, which we can optimize, so-called quality metrics. And sometimes they call it aesthetics, yeah, because they kind of correlate with notion of aesthetical appearance. And the example of those are number of crossings. So for instance, compare this ugly drawing where you have many intersections and this where you don't have any. So this is something you want to optimize, yeah, to make drawing more readable. Another such quality metric is the number of bends. Yeah, so if you are talking about a polyline drawing, then you want your edges to bend as little as possible, because when they bend a lot, becomes very hard to actually follow them. Another quality metric is the area. So usually we want that our area is not too big, because this drawing is to be displayed somewhere, is to be printed somewhere. And so we want to make drawings compact. Then another example is a crossing resolution. Yes, so for instance, if we have two edges crossing, so we cannot avoid crossings, but still, if we have crossings, we don't want these crossings to have very tiny angles, yeah, because the smaller is the angle of intersection, the harder it is to distinguish these two edges. Yeah, so we want that all crossings are close to 90 degrees. And another type of quality metric is a so-called stress of layout. For instance, if you have two vertices and these vertices are connected by some path in the graph, what you actually want is that the distance between those vertices is somehow proportional to the graph theoretic distance in the graph. So this is a different type of a metric. I just want to show you that there are many metrics and they have different characters. Some of them are simple, defined by geometry, and some of them are more complex. You have to look at the graph structure. So this is just some example. There's a lot of different quality metrics that people came up with. Of course, as you understand, none of these metrics by itself really describing the human perception. Yeah, so they are too simple to describe what actually human thinks is nice. And people try what researchers try to do. They try to combine those metrics. Yeah, so let's say taking a linear combination of those, and then optimize this linear combination. And by the way, I mentioned before this graph drawing competition. It is one of the parts of this competition is that students or participants are given a quality metric, and they have time to construct algorithm that is optimizing this quality metric. But I will mention that competition a bit later again. So now the third way of formalizing graph drawing problem are so-called partial constraints. Yeah? So before we had the drawing conventions, which were hard rules for the whole drawing. And the partial constraints are those, again, hard rules, but for a subset, yeah, for subset of elements. So I will talk a little bit about that again later. So to go back to the graph drawing problem, it now can be formalized like this. I'm given a graph and I want to construct a drawing. Now I know what a drawing is, such that it complies with some given conventions. It optimizes some given quality metrics, and it satisfies given partial constraints. So this is absolutely formally defined now a graph drawing problem that we can study both mathematically and algorithmically. So this is at the end of the first part of my talk. And if you have questions on graph visualization itself, on the field of graph visualization, whatever I mentioned until now, maybe you want to ask at this point. Okay, so nobody, then I just keep going. Now I want to talk a little bit about my research in the field. So generally, you understood that I'm working on algorithm for network visualization, but these studies have totally different perspectives. And I personally look at 4 different perspectives. And the first one is theory. And I gave you now a formal definition of a graph drawing problem. And usually a problem in theory looks like, given a class of graphs, either is a fast algorithm that constructs some kind of nice drawing when a nice drawing is formally defined. And let me give you some examples of problems that I have studied. Yes, so I've mentioned those partial constraints, yeah? And I've studied several problems about partial constraints. For instance, let's consider the following application. We have, let's say, a graph drawing on a tablet, and the user comes and says, yeah, I want those vertices to be drawn on a line. Yeah, so I want the same drawing, very similar drawing, but those vertices being drawn on a line. How do we do this algorithmically? Yeah. This is one of the questions that I have studied. And these are examples of 4 different papers studying this kind of constraints. So for instance, here we are given a graph, yeah, part of which is already drawn on the plane. Yeah, so the black part is already drawn and the gray part is not drawn. Yeah, so what we have to do, we know that the whole graph is planar, so we can draw it without intersections. And what is asked to do is actually to construct the drawing of the remaining graph. Yeah, so this is the drawing of the remaining graph. Another very similar problem is when you are actually again given a part of the graph drawing, but now you are allowed to do bends. Yeah, so you are allowed to use polyline instead of straight lines, as here. Another set of works is exactly the application I showed you before. So you're given a graph, like an abstract topological, let's say, graph, and you're given a set of vertices. They say the one which is collected by the pink curve and the one which is collected by blue curve. Yeah, and you want a drawing such that vertices on the pink curve and on the blue curve lie on a line. They are aligned. And let's say another set of works was that now we have, again, a planar graph, and we have a subset of vertices, which is already fixed on the plane. So it differs from this setting because here we had that subgraph, which is already drawn on the plane, is kind of connected. And here is just an independent set of vertices, which is fixed on the plane, which makes the problem very different. So this is kind of examples of problems with constraints that I have studied.
I mean, is this at all tractable? Because it seems, I mean, very extremely difficult mathematically to find any kind of general theory to such, I mean, things, constraints. I think it's mathematically must be very challenging.
It is very challenging. Many of the problems, the decision problems that you get of this are NP-hard problems. So probably they are not polynomial algorithms. If you restrict very much the class of graph that you study, you find some polynomial algorithms, but many times proofs are very detailed and very involved. So it is mathematically challenging. That's true. So this is theory. Yeah, I talked a little bit about theory. I will go back to theory when I'm talking about the geometric problems later. Except for theory, I also look at the experimental questions. And in experimental questions, we usually ask, so we have some algorithm, yeah, we implement it, and then we run it on many instances, and we evaluate those instances according to our quality metrics, to some quality metrics. And then we compare, you know, among different algorithms, among different instances, how those algorithms perform. So this is kind of experimental research, and usually it's also based on quality metrics. Not all experimental research is based on quality metrics. Sometimes it is, you just construct different drawings and you look at them, yeah, and you intuitively assess that this one is better than the other one. Or you, if you show to users, to people, and do an empirical study, then I actually say that this is not experimental research. It's kind of experimental, but I call it empirical then. Okay, so a little bit about experimental research that I have done. This is very much connected to this graph drawing contest, which is a competition that happens during the graph drawing conference. The graph drawing conference takes place in September, and every time it changes location. So around 10 months before the conference, so the graph drawing committee, now I'm part of this committee, announced a quality metric. Yeah, so the exact setting in which graphs have to be drawn and the quality metric that have to be optimized. And the participants have time to implement the algorithm and test them. And then during the conference, they have 1 hour and they're given 10 instances, and they have to run their algorithm on these instances. And then, you know, usually the quality metrics, the committee compares the results of the participants. So this is the automatic, so-called automatic challenge. There is also a manual challenge. People who attend the conference in the good times when we had a real conference, they can actually manually move the vertices in order to optimize quality metrics. And this also was a manual competition. Yeah, so actually, before I became part of the committee, I was doing a graph drawing course in Karlsruhe, and I saw this as a very nice way to bring students to work on some research problems. So I gave them this challenge, and they were implementing algorithms, and we participated in this automatic category. Not only that, but we actually came up with very interesting novel ideas on algorithms, and then we even could publish papers. Yeah? So we made this to papers later. And the one such example is the following setting. So this is a purely topological problem that have been a part of this graph drawing contest some years ago. So we are given a graph, yeah, and what we want to do, we actually want to draw it in a book. Yeah, so book is such a topological structure, and you are asked to put the vertices on the spine of the book and to distribute edges to the pages. So the edges on the pages either are not allowed to intersect, or we want to distribute the edges to the pages in such a way that the number of crossings is minimized. Yeah, and that was the quality metric of that challenge. So we had to construct book embedding into book with a given number of pages, and to minimize the number of intersections. By the way, this problem comes, it's a way, a try to formalize some VLSI layout problems. Yeah? So when you have different layers of those cables, and you want to kind of that on every layer you have as few intersections of cables as possible. The problem is hard, so it is NP-complete already for 2 pages, and it is equivalent to testing whether the graph is sub-Hamiltonian, yeah, whether it has a Hamiltonian path. And what we did in that work, we implemented multiple heuristics. There's a number of heuristics in literature. We implemented those. We came up with some new, and then we did an extensive experimental evaluation. So what you see here is kind of a visual way to show how our algorithm worked. Yeah? So we have that every color actually specifies a different algorithm. And here we have the number of pages, and here we have the number of vertices, and we can see how what we see is that as you grow in number of vertices and the number of pages, the best performing algorithm are changing. Yeah, so you cannot say in general that this algorithm is working best, but what we see here is that depending on the complexity of the problem, we have different algorithms that perform best. And what you see here that every cell is divided into 2, because actually this problem has 2 subproblems. The first subproblem is how do you place the vertices on the spine, in which order, and the second subproblem is how do you distribute edges to the pages. Yeah, so these are kind of 2 different logics, and this tile is divided on 2 because this one part saying which algorithm we use for the distribution of vertices of the spine, and the other part is saying which algorithm we use for distribution edges to pages. Yeah, so this is an example of experimental work. And something which is totally different, but also kind of experimental. We try to use machine learning to model a quality metric. So something that I'm personally always not satisfied with is this very strict definitions of quality metrics that we have, and that the fact that they never approach modeling the human perception. Yeah, and what we try to do in this work, we try to use machine learning to model this kind of quality metric. without restricting on what exactly it depends. Yeah, not saying that this is number of crossings or some angles, but trying to measure different features in the drawing and then training this quality metric, which is actually arbitrary polynomial functions of these low-level features. And the particular problem that we addressed in that work was, if I give you two drawings of the same graph, can machine learning system decide which one is actually has a better quality without defining exactly what is a better quality? Yeah? And this was, of course, a data-driven approach. So we had generated a large data set using algorithms again. So we started with a nice drawing, which constructed by some algorithm we trust to, and then we spoiled that drawing. So we started flipping vertices, bending edges in order to get drawings which are less nice. And this way we got many pairs of drawings where one is better than the other. And then we gave these to this Siamese neural network system and we trained this quality metric. So what we have actually seen that comparably with other quality metrics, it performs better. So this is a nice thing showing that, yes, we probably can model the notion of, let's say, niceness, readability using machine learning. But the downside, of course, of this is that this is an arbitrary polynomial function. And of course, optimizing it, like using it to construct nice drawings later, is a very challenging question. So for this paper, we got the best paper award in graph drawing in 18. And the last, no, not last, pre-last aspect. So next to experimental research, I've done also some empirical research. And let me give you outline this empirical research. So here we have a totally different perspective. Yeah, so we actually get perspective of people. Yeah. And the question that we investigated with psychologists, so they have Klaus Christian Carbon and Markus Raab, they work in the University of Bamberg in empirical aesthetics. So what we studied with them was the following. If we change only the outline of the visualization, does this somehow change how people perceive it? Do people think that maybe this one is nicer than this one? Yeah, so they would try to keep the inside as similar as possible, which is a challenge algorithmically, but we tried. And we only change the outline. And so we asked people.
He likes the first one.
Yes, I can tell you the outcome. So we had dependent variables. Our dependent variables, the things that we asked people was beauty and interest. And our independent variables, so what we tried to vary was curvature and complexity of the outline. Yeah, so this is more complex than this. Yeah, and this is more curvy than this. Yeah, and so what we found is that the perceived beauty, so how people perceive the node link diagrams, is influenced by the curvature of the outline. Yeah, so the more curvy, the more beautiful they think it is. And if we ask about interest, we see that the interest is influenced by the complexity of the outline. So if the outline is very simple, it's like just a circle, it's not interesting. But if it starts having some complexity, then it's getting more interesting. So these findings are completely in line with other findings, let's say about shapes of cars, yeah, and shapes of other household objects. Yeah, it was just a kind of different work, taking a user perspective, and also this completely aesthetics perspective. So here, because at least not network visualization is not about beauty only, right? But here we went a little bit to this saying, okay, so what people think is beautiful. Yeah, and the final aspect of my work are applications. And here we have usually real data coming from real applications, and we want to visualize it so that we give some outcome back to people and only do our science. And in this direction, I'm doing the following work. I collaborate with philosophers who study large debates. And actually, what we did with these philosophers, we have gathered a large amount of data on what people think about being vegetarian. So we asked them 100 questions on different aspects of being vegetarian. And what you see here on this visualization, this is not a geographic map. This is a conceptual map. So what we have is that every vertex is actually an opinion. An opinion is a way to answer the survey. Yeah, and we have some opinions are large because many people have the same opinion. Yeah, and some opinions are small because only one person holds this opinion. We have opinions connected by edges because these opinions are very similar. And what we actually do, we draw it on the plane, this network of opinions, and then we cluster it. So we partition it into pieces. And then we use so-called Voronoi diagram. We partition the plane into regions and then color these regions according to the cluster color. Yeah, so this way we get this very nice geographically looking map, but it's actually not nothing to do with geometry. Every country is a set of opinions which are similar. So we have vegan land, all those opinions which are actually about being vegan, Vegetaristan, about being vegetarian, Moderatia, where people do eat meat, but with a moderation. And we had these maps playing live in a museum exhibition that was actually the nicest part of it for almost a whole year of 2017, 2018. This map was displayed on a large screen in a museum, and people could come and fill in the survey, and they would see themselves on this map. Yeah, so people enjoyed interacting with this map. And right now I continue that, and I'm looking at different data sets, and it's about European values. So the data set is called European Value Study. It's 250 questions, which are, this study is a repeated study, so the data being collected all the time, and they are freely available online. And instead of doing geographic maps for this European Value Study, we try to do the conceptual maps and see how opinion of people are similar across Europe on different values. And this is a really deep study. It's about all kinds of values, like political and regional and family, and covers all different aspects of life. So this is the applied side of my research. And maybe you want to ask questions, because from now on, I will dig very deeply into, a subset of the problems I have worked on. And it will be very theoretical from now on. So if you want to ask something about this more, let's say, high-level aspects, it's a good moment.
So I noticed Turkey was really dark in the map you showed on the previous slide. So what was the reason for that?
What is the reason to do these maps?
The Turkey is very dark.
Sorry?
The Turkey on the map, Turkey, the country Turkey.
The Turkey here on this map.
It's dark.
This one, this map, it was about working preferences. So how important is work? That, actually by this picture I wanted to show is that using these geographic maps, you can only visualize one concept. Yeah, and here they visualized answer to the question, how important is work for you? And it seems that in Turkey, work is really important. That's, yeah.
In Georgia, it's not important at all, right?
Yeah, you see, I think Georgia is not one of the countries where the survey is conducted. By the way, this can be corrected. I think if we contact social researchers, sociologists in Georgia, maybe they are interested to participate in this study as well. Okay, so now I dig into theory, and I'm going to talk about geometric problems in graph drawing. So as you understand, graph drawing is all about placing points and drawing lines. So it is very geometric in nature, but sometimes it can be topological. So sometimes it is about like this book embedding problem, yeah, where you have vertices on line and edges on pages, then it becomes topological, right? It's not geometric anymore. But now I'm going to talk about geometric problems when you really have geometric points and real polylines. And the subset of these geometric problems is so-called point set embedding problem. So let me now define what is a point set embedding problem. So in a point set embedding problem, you're given a set of points, yeah, which initially we assume, let's say we have endpoints on the plane, and we have a planar graph, so a graph that can be drawn on the plane without intersections with n vertices. So we have the number of points is equal to the number of vertices in the graph. And what we call point set embedding of a graph on the point set is a bijective mapping between the vertices and the points. So that, yeah, so this is a mapping. I have mapped my vertices, yeah, my vertices to the points. But we want this mapping to be such that if I draw my edges by straight lines, then I don't have any intersection. So that's why we call it planar point set embedding. Yeah? For instance, if I would decide to swap these two vertices, yeah, then I would my embedding would not be planar. Yeah? So imagine this vertex moving to this point and this vertex moving to that point. Yeah? Then the embedding is not planar. So that's not what we want. We want that our embedding is planar. Okay. So this was the point set embedding notion by itself, yeah. And what we now actually want is so-called universal point set. So a set of points on the plane is called universal for a class of graphs if there exists always a subset of points where we can construct a point set embedding of any graph in that class. Yeah, so if you give me a class of planar graphs, a set of points for this class of planar graphs is universal if I can find a subset in this point set where I can embed my graph in. And the question is there is a set of points that is universal for all planar graphs? Yeah, so again, I want to find the subset where I want to draw a graph in. And it happens that actually, if you take a round of n square points on the grid, that line on the grid, then you can embed there any planar graph with n vertices. Yeah. So that's actually says us that yes, you can bound the size of universal point set by a function which is like around n squared. There's some constant there. That's why we have this O notation used, because it is 2n squared minus 4, something like this. And a big open problem in graph drawing and in computational geometry fields, because this is also like real geometry, is whether there exists a set of smaller than n squared points, like asymptotically smaller, meaning maybe n log n, maybe n square root of n, something which is expressed by a different function than n squared with constants, which is universal for planar graphs. Okay? So this is a big unanswered problem. And I can give you some results that exist on this problem, so not all of them. For instance, what is known is that if you have a graph which is outer planar, so outer planar is again a planar graph, but it's much simpler structure. It is such that all the vertices, you can construct a drawing where all the vertices are incident to the same region, yeah, to the, let's say, outer region. So we have actually all vertices lie on a cycle, and inside we only have chords. We have like edges. So if you have such a graph, then any set of points, of endpoints in general position, I'll define what is in general position, is actually universal. Yeah. So we can always draw a graph on a set of points of the same size. And by general position, I mean that no three lie on the line. So here you see that these three are almost on the line. Apparently, when you start dropping points on the plane, it's very hard to avoid this all three lying on the line condition. Yeah, so general position, from now on, I will use this term without repeating the definition. No three on the line. So there are other results for other subclasses of planar graphs. So for instance, we know that there exists a universal point of size n log n for so-called two-outer planar graphs. And let me describe you what a two-outer planar graph is. It is a generalization of outer planar. So we have the outer layer, which is outer planar. And if we remove this, we have another one. And what remains is again a set of outer planar graphs. Yeah? So like two layers of outer planar graphs, one inside the other. And this proof, n log n, so this is a paper that part of this proof is in the paper where I participated. It took us many months to prove. It's really, really complicated. So, and we know that the approach that we took is not extendable further. So we cannot even extend it to three outer planar anymore. There is another result which says again an n log n universal points that exist for bounded path width graph. So what is the path width? I don't want to define, but this is a kind of graph which has a path structure. Yeah, so it's not just a path, but it's kind of a set of faces which are arranged in a not very let's say deep structure. Yeah? So you don't have a very like the high width, but the width is very low, and then faces follow one after the other, like in a path way. And another result, it's n to the 3/2 log n, the size of the point set, for plane 3 trees. So this is a beautiful family of planar graphs, which is constructed in the following way. You take a triangle, you put a vertex in this triangle, you connect it to all these three vertices or a subset of them, then you again repeat this procedure. Yeah, you put a vertex in the triangle, connect. And this nice structure of plane 3 trees allows to do many proofs. So it has this inductive way to construct the graph, and it really helps to do proofs. So many algorithms are known for plane 3 trees for the problems which are actually NP-hard for planar graphs in general. So these kind of partial results. There are other partial results, but I stop here. And there is a variation of that problem, actually many variations of that universal point set embedding problem. But one of the interesting variations is when your graph is actually directed. Yeah, and when the graph is directed, what is very common in graph drawing is to ask, can you actually draw this graph so that all the arrows, yeah, so the directed edges, they point up? Because if they point up or right, then they kind of have the same direction. It's easy to realize the hierarchical relationship in the graph. Yeah, so we like to draw these upward directed graphs in an upward way. So now the input to the problem is a point set and a graph that can be drawn upward planar way. And the upward point set embedding is again a bijective mapping, so that the resulting drawing is not only planar, but also upward. Yeah, so all edges are straight lines, so such that the source, the start of the edge is below the sink. And again, the same way we can define a universal set, a universal point set for upward planar drawing exactly in the same way. And narrowing down even further, I've shown you some results for planar undirected graphs. Yeah, but for directed graphs, actually we have much fewer results, and we didn't even look at very complicated graph families. So we know things about paths, trees, and outer planar graphs. That's all we know. And here I concentrate only on paths because that's actually the result I want to talk about today. So an oriented path is just a path where the edges are oriented in an arbitrary way. Yeah, and you can see that an oriented path is, of course, an upward planar graph, because you can always shift a little bit the vertices so that the resulting drawing is actually upward. So the question now is, how many points do I need to take in general position so that every oriented path has an embedding on this point set? Yeah, is this number somehow limited? Can I limit the number of points that I actually need? Yeah, and then that's how the embedding will look like of path and the point set. And the theorem that I actually want to prove here is, apparently, if you take any set of n-1 square plus 1 point in general position, this set is going to be universal for the family of oriented paths. Before I go to the proof of the theorem, by the way, what is the time? I don't have the time in front of me.
Time, you still have 15 times. It's 50 minutes.
15 minutes. Okay, excellent. I want to tell you about some results that we knew before this proof came. So what did we knew? We knew that if we have an n-vertex oriented path and we have a set of points in convex position, yeah, then an embedding always exists. So convex point sets are really good. We can embed their path of the same size. Yeah, but of course, there's still we still had the question, what happens if point set is in general position? It doesn't have this rigid convex structure. What we also knew is that if we limit how the path looks like, yes, so we say it has only one sink, so it has a single vertex with only incoming edges, yeah. So then actually embedding is quite trivial. So you take the highest point, you rotate the line around that point, you partition your point set in such a way that on one side you have so many points, on the other side you have so many points, and then you sort your points according to y coordinates. So embedding such a path is like really trivial. But if we expand a little bit more, we say, okay, this is such a path that you have a monotone path going to the left as long as you want, and then one edge to the right. Again, many edges, one edge. Yeah. Apparently, this one is also always possible on endpoints, but the proof is much harder. And then we know a couple of other paths which have a bit more general structure. Again, many going to the right, one to the left, one to the right, many to the left. So here is this abstract way of giving this path, but a very, very restricted small families of paths. Well, we know that embedding is always possible. A couple of papers about that. And we also know before that we knew that if we take n times 2 to the k points, yeah, so k is the number of switches. Switches are those vertices where the direction changes, yeah. So, but this is exponential in k, yeah. We know that the embedding is always possible, and the algorithm is kind of simple. What you do is that as long as the path is going in one direction, you are sorting your points by y coordinate, and then one before the moment when the direction is going to change, you are going to the highest point. Yeah. Then you look where you have more points on the left or on the right, and then you recurse there. So that's wonderful. So simple algorithm to get this exponential number of exponential bound. Okay, so what I actually wanted to tell you that we had some results, very restricted results, because before actually this idea came, and this proof came of n-1 square plus 1 points in general positions are universal for oriented paths. And let me explain you how the proof is actually working. So the main idea is to partition the point set according to convex layers. So you take a convex hull, you remove it. You take another convex hull, you remove it, and so on. So sometimes they call it potato peeling. Yeah, so you take different layers of peels. And the main definition that I need to give is this notion of visibility between the layers. So for instance, from this vertex, I can see that vertex. means that I don't intersect this convex hull when I connect to that vertex. Yeah, and from this vertex, I don't see that vertex. So these vertices are not visible to each other, because if I take straight line, I do intersect the convex hull. Yeah, so this is visible, this is not visible. And the first observation is that if I have a set of n-1 square plus 1 points in general position, then if this point set doesn't contain a convex subset of n points, then it has at least n layers. So this is a simple counting. Yeah. So if I assume otherwise, that I don't have such a subset, the convex subset with n points, yeah, then I get fewer points, kind of counting all together, I'll get few points that I assumed initially. So now I have two possibilities. Yeah, this proposition actually says that I have two possibilities. Either I have a subset, a convex subset with n points, or I have at least n different layers. So if it happens, so this is, let's say abstract visualization of this point set, and it happens, like the first possibility, it happens that I have a large convex subset, yeah, a subset with n points. Then using previous work, we know how to embed paths on that subset, yeah, just using previous work. I don't want to go into details, but it's apparently quite simple to do that. You just take the lowest point and the highest point, divide the point set, find the right edge, which also divide the path into two parts, and then embed one part on one side and another part on the other side. So now I'm going to the second case when I have at least n different layers. And my main aim is to place every vertex on next layer. So I'm not ambitious at all. I'm just saying I'll be using only one vertex of every layer. So if I manage to do that, use one vertex per layer, like 1 point of each layer, then I'm actually, I'm safe. Yeah, I have enough layers. And we will be violating this rule of jumping from layer to layer only if we don't have the visibility. Yeah, if by jumping to another layer, we happen to cross the layer on which we are right now. And these are our invariants, the invariants of the inductive proof. So we assume that this is always happening. So this is proved by induction. I have to show the base case. Yeah. So in the base case, let's assume that the first edge is going to the right. It's directed from first vertex to the second. Then I'm going from sink of the first point set to the sink of the second point set. Sink is the highest point. Yeah. That's what I'm doing. If it's directed opposite, yeah, then I'm actually doing this. I'm going from the source of the second point set to the source of the first. Okay, so now by induction hypothesis, I assume that I have already placed k vertices, yeah, and I assume that my induction invariants hold. Yeah, so I've been only jumping between the layers. I didn't jump between the layers only when there was no visibility. And let's assume we have the first case when now I'm going to place the vertex vk plus 1, yeah, in my induction step, and I look how the two previous vertices look like. So the vertices vk minus 1 and vk are placed on different layers. Yeah, so it looks like this. And let's assume that the vertex vk plus 1 is connected by the edge from vk to vk plus 1. Therefore, we are searching for a point on the next layer which is higher than vk. Yeah. But it can happen, of course, that this point is invisible. Yeah. So we have this situation. So if the point is visible, then we just place vk plus 1 on this point, and our induction step is finished. But if not, yeah, then we cannot place it there. So we place it over here. Yeah, we place it on the same layer. Okay, so that was the case one when vk minus 1 and vk were placed on different layers. Now assume that vk minus 1 and vk are placed actually on the same layer. Yeah, so we have something looking like that. So if the h vk plus 1 is going to the right, yeah, then we are exactly as in case one. We are using the same layer if we don't have visibility, and we are using a different layer if we have the visibility, and there is definitely no intersections because things are partitioned, you know, our edges are partitioned by the layers. But the problem starts, yeah, so when we have the following. So the edge vk minus 1 vk was directed in to the left, yeah, and we have it lying here on the point on one of the layers. And the next vk plus 1, yeah, happens to be invisible. Yeah, so like we came here. If vk plus 1 is visible, we can go here. Yeah, but if it is invisible, then we would have to go over here. Yeah, and we would get an intersection. And here is the interesting trick. So let's assume that this point is invisible from vk. Yeah, but why did we put vk on the same layer with vk minus 1? It was exactly because this point was invisible from vk minus 1. So what we actually now getting is that our partition in the convex cell was not, if we assume that this happens, is that our partition in the convex hole was not correct. So this cannot happen. If vk was invisible, so this point was invisible from vk minus 1, it means that this point is going to be visible from vk. Yeah, so because if we assume that it's there, then we get, you know, there's some problem in partitioning. So we did wrong our partitioning. So that's why we can always place vk plus 1 and our inductive proof finished. You know, that's kind of technical details of this proof, and using some visibility notion. So the main open problem that we have here is how to decrease the n-square bound. Yeah, so we know that around n-square points are enough, but can we do less? And apparently we don't have a counterexample saying that, so if you take a point set of endpoints in general position, there exists an oriented path which doesn't have an upward planar embedding on this point set. Yeah, so we don't have a counterexample. And one of the reasons that we don't have a counterexample is an embedding of a path, an upward embedding of a path can be very complex. So it's not necessarily like X monotone, right? It can be as complex as this. It's folding inside, folding out again, wiggling around, and so on. So yeah, that's many groups around the world have tried to answer this question, and till now unsuccessfully. So I'm really curious what will happen with this. I will be following the progress of this problem. So thank you very much for your attention.
Yeah, thank you. It was a great talk, very interesting. Let me stop recording and we now move to the questions.